Welcome to the second module of the first week. So, let us begin with the recap of what we did in the first module. We started by motivating ourselves with a physical pendulum like the one that I still have here with me. The central piece of physics was that for oscillatory behavior and in the limit of small oscillations. It is very important that we need to stick to the limit of small oscillations, and if you do so, we figured out that restoring force is proportional to displacement with the negative sign. Again, this negative sign is very crucial, we need it for oscillatory behavior. So, that this statement that is written here is the central piece of physics, which will ensure that finally, when we get to the solutions will display oscillatory behavior. Now, starting from this piece of physics, we finally wrote down equation of motion, which turned out to be a second order differential equation of this type. So, it is d square x by dt square plus omega square x is equal to 0, where this quantity x is the displacement. So, for instance, in the case of this physical pendulum that I have here, so this rest position would be our equilibrium position, and I make a small displacement away from the rest position. The distance from the equilibrium position to the new position would be my displacement. And this quantity omega we already saw, we already met this quantity, and this is simply the angular frequency. It is 2 pi divided by the time period t. So, we did not solve this equation in the last module, but we know that solution would imply that I should be able to get this quantity displacement x as a function of time. So, that is what I would mean by saying that I have solved this problem. So, in this module we are going to get the solution for this equation. So, one could take a hard way by actually solving this differential equation, but here in the spirit of what we did in the first module, we will try and guess the solution motivated again by the phenomena that we see. So, if you look at the phenomena that we are trying to describe and for which it appears that the equation of motion is what I have written down here, you will notice that this is an oscillatory phenomena. So, any solution for this oscillatory phenomena should somehow capture this oscillations. In other words, the solution mathematically should be a function that oscillates as well. So, we are looking for functions that would oscillate, and they probably could be possible solutions for this problem. And again, the motivation for such an argument is that because physically we see that the pendulum is oscillating, okay, or in general whenever you have restoring force that is proportional to displacement with this negative sign, the solutions are expected to be oscillatory. So, I am looking for solutions which are oscillatory in nature. So, let us begin by guessing some solutions. So, one of the simplest possible oscillatory functions that we know are the sines and cosines, the trigonometric function that we studied in schools. For example, I can make an ansatz, a guess of this type, that x of t is sin t. So, the problem with this guess is that the dimensions do not match. On the left hand side, the dimension is that of length, because x is displacement and it has dimensions of length. But on the right hand side, I have t which has dimensions of time, and of course, it is embedded inside a more complicated function which is sine function. So, clearly there is a mismatch of dimensions. So, we need to correct it. So, one possible way to correct it is to make a small adjustment here. So, let me say that my x of t is sin omega t, and I know that from what we had seen earlier, omega is simply 2 pi divided by t, and this has dimensions of inverse time. So, when I put in omega here, the time and inverse time, they would cancel one another out. So, this will essentially be a number, and in that case again there is a dimension mismatch, because on left hand side x has dimensions of length, but on right hand side you have something that is dimensionless, but that can be easily fixed by adding this a here, and a we can guess from what we have written down should have dimensions of length, and for our purposes that is simply the amplitude of the oscillation. And left hand side of course, you have displacement, that is a function of time. So, amplitude would be something like this. So, this is the rest position and this could be the amplitude, the largest displacement that is possible. Now, that we have actually guessed a possible solution, next we need to check if this is indeed the solution for this problem. So, let me now assume that I am going to work with this solution, let us say is a sin omega t, and if it is indeed the correct solution, if I plug it back into this equation, it should satisfy the equation, and it is very easy to do. So, x of t is a sin omega t, and dx by dt will be a omega cos omega t, and d square x by dt square would be minus a omega square sin omega t. Now, let us put the quantities back in this equation, in which case I will get minus a omega square sin omega t plus omega square, which is this quantity, and x is a sin omega t, and clearly this cancels one another out. So, you do get a 0. So, we have discovered one solution for our differential equation, x of t is a sin omega t. We saw that we found out one solution, which is a sin omega t. The question is, are there other possible solutions? Without even much thinking, could say that maybe cost function is also a possible solution. So, I could have by the same argument written down that x of t equal to, let us say, some b cos omega t could have been a possible solution, and in fact you can verify that b cos omega t is another possible solution as well. So, the hint for all this comes from the fact that the differential equation that we started with, d square x by dt square plus omega square x equal to 0, is a second order linear differential equations, which means that in principle it should have two independent solutions. Let us say that I have two possible solutions for my differential equation, which could be x 1 of t and x 2 of t. So, when I say that x 1 of t and x 2 of t are linearly dependent, I am making the following statement, that x 2 of t is equal to some constant times x 1 of t. So, in that case, once I know x 1 of t, all I need to do is to simply multiply it by a constant, I get x 2 of t. But in this case, what we require is that the two solutions should not be related by this relation. If they are not related by this relation, then you would say that the two solutions are indeed linearly independent. And again this is something you could verify for yourself, that sin omega t and cos omega t are indeed linearly independent functions. So, at this stage what we have is, we were trying to find solutions for a second order linear differential equation, and as dictated by the mathematics we have found two linearly independent solutions. One of them is A sin omega t and the other one is B cos omega t. So, in fact, you need not stop with this. In fact, you can also show that if I add A sin omega t and B cos omega t, that would also be a solution. I am not going to do that, it is very easy, and just the recipe that we did here in the previous case. If you follow that, you should be able to show that x of t being A sin omega t plus B cos omega t is also a solution. At this stage, we have a combination of two linearly independent functions, sin omega t and cos omega t, with two arbitrary constants A and B. We will see how to determine them a little later, but this combination is a possible solution to the differential equation that we had obtained for describing the oscillatory function. Now, another question is this the most general function that would be a possible solution? The answer is no. You can actually generalize it even further by adding a phase term as shown here. So, this phi that is written here is the phase, and we will see what this phase is about. To understand phase, let us cut down the second part and just stick to this simpler version of our solution. Now, to understand phase here, let me also for comparison write down x of t equal to A sin omega t. Now, both these are possible solutions to our differential equation. In one version I have written down A sin omega t, and in the other I have written down A sin omega t plus this added function phi, which I am calling the phase. So, to understand how this works, let us plot the solution. So, I am going to plot displacement x of t as a function of omega t. So, let me first plot this function x of t equal to A sin omega t might look something like this. So, this is your 0, pi and 2 pi. Now, let me also plot this, but before plotting the second one, let us say that at t equal to 0, x of t corresponding to this case would be A sin phi. On the other hand, corresponding to this case, at t equal to 0, x of t would be equal to 0, or x of 0 would be equal to 0. So, they differ in their values at time t equal to 0. So, if I have to plot this function now, let me plot it with the black pen. At t equal to 0, it is a non-zero value, A is not equal to 0 and phi is also not equal to 0. So, let me say that at t equal to 0, this is my initial point, and this is going to be something like this. Okay. And to complete the picture, let me draw it on the negative t direction as well. Okay. So, you could see that phase is basically this quantity here. So, it is the initial offset that you give with respect to a solution whose phase is 0. So, for the case of this red curve here corresponding to this solution, the phase was 0. On the other hand, corresponding to this solution, this one, your initial phase was phi, and that corresponds to this quantity here. It can be easily realized that if phi were 2 pi, you are moving an entire distance corresponding to 0 to 2 pi, and there would be no difference between a solution that has no phase and the one that has a phase difference of 2 pi. So, with this understanding of phase, let us put back the complete or the most general possible solution. So, I have written down the most general possible solution here as displacement as a function of time is a sin omega t plus phi, and there is also the second linearly independent function which is b cos omega t plus phi, and as we just saw, phi is simply the phase and a and b are the amplitudes. And if phi is equal to 0, the solution would simply reduce to a sin omega t plus b cos omega t, and these three numbers a, b and phi are arbitrary constants. And the information about this values of a, b and phi will have to come from the system that one is studying. It is not determined by the equation of motion itself. If you go back to the equation of motion, you will notice that there is no information about initial values in the differential equation. That has to be provided as part of the problem. So, these three quantities would be in general called initial conditions. So, if you want to get a specific solution for a particular problem, you need to specify these initial conditions. So, in the tutorial section, we will see how these initial conditions can be provided and used in obtaining the solutions. Now, let us get back to our solution once again. So, I will stick to one form of this solution, which is a sin omega t plus phi. So, that is my solution for displacement. Now, starting from here, once displacement is given, it is easy for me to calculate the velocity. So, I can write an expression for velocity which will be dx by dt, and if I differentiate, that would be a omega cos omega t plus phi. And given the velocity, it is again straightforward to calculate the acceleration, which will be d square x by dt square, or second derivative of displacement with respect to time, and that would be minus a omega square sin omega t plus phi. So, if you notice the relation between the displacement and acceleration, you will notice that displacement and acceleration are proportional to one another with the negative sign. That should not be surprising, given the fact that we actually started from an ansatz which basically stated that restoring force is proportional to displacement with the negative sign. So, this is a sort of consistency check. From that ansatz, we went to write down a differential equation, and from there we obtained the solution, and finally we see that it is indeed consistent with the ansatz that we started with. So, to have a pictorial understanding of these three quantities, again let us plot these functions. So, let me start with displacement as a function of omega t, and for the purposes of plotting sketching this function, I am going to assume that phi is equal to 0. just a simplifying assumption, and I am also going to assume that the amplitude A is greater than 1. I will also assume that omega is greater than 1. Now, let us sketch the function. So, this is x of t, and the same scale, let me see if I can plot velocity, which I will call v of t. So, this will be v of t as a function of omega t. So, this is a cosine function, and I have assumed that a and omega are greater than 1. So, it is going to look something like this. This is of course your pi and 2 pi. Let me also sketch acceleration as a function of time, and this, as we see here from the figure, will be negative of displacement. So, I should have something like this. So, this is 2 pi, pi and 0. Let us pictorially look at the solution and what they really reveal. So, I have sketched displacement, velocity and acceleration as a function of time. So, let us see what they physically tell us. So, the first thing to notice is that at the point where say the displacement is a maxima, that is precisely the point where the velocity is a minima, this point here. Okay. So, how do we relate it to a real physical system like this? So, this is how say my pendulum oscillates, and if I look at it carefully, the displacement is maxima at, let us say, somewhere here, and that is precisely the position where the pendulum comes like this, momentarily stops and then turns back. So, that is exactly the position where the velocity is 0. So, at the position where the displacement is maxima, the velocity is 0. On the other hand, you can easily figure out that as we pass the equilibrium position here. So, this is the equilibrium position. When it is oscillating, it passes through the equilibrium position, and when you pass through the equilibrium position, its displacement is 0, but nevertheless its acceleration would be a maximum. So, at the extremes where the velocity is actually changing signs, because it is changing directions, velocity would either go from negative to positive or positive to negative. So, the acceleration would be largest. So, at the point where the displacement is maxima, the velocity at the corresponding time would be 0, and at precisely the same time the acceleration is a maximum. So, that is this position at the extremities, either at this end or at the corresponding end on the other side. On the other hand, if we analyze what happens, let us say at this point here. So, here the position is 0, but the velocity is maximum, and that is understandable because really the pendulum is passing through the equilibrium position and its velocity is the largest, and here there is no change of direction, there is no change of sign in the velocity. So, in this case acceleration is indeed 0. So, the velocity would be maxima corresponding to this, and acceleration would be 0. So, it would correspond to this. So, essentially what we see is that at the positions where displacement is maxima, your velocity is 0, and at values of times when displacement is 0, velocity is maxima. And displacement and acceleration have this relation that they are proportional to one another, and there is a minus sign between them. So, we see that clearly in this sketch. Next, we will try and evaluate the kinetic and potential energy of this of an oscillating system. And again, the starting point is we will start with one possible solution, and I have taken one of the simplest ones as a sin omega t plus phi, and it is even more simpler if I can even set phi equal to 0, it would not change any of our results. The kinetic energy is easy to write down. So, kinetic energy, which I will indicate by K E, is simply half times mass into the velocity square, which will be half mass into dx by dt whole square, and that is simply half m into a omega cos omega t plus phi, and this has to be a square omega square and cos square. What about the potential energy? Potential energy is simply the work done by the system against the restoring force. So, this at this position we have assumed that the potential energy is 0, because we have set the sort of put the scale such that the 0 of the position corresponds to the point where the pendulum does not do anything if left to itself. So, that will be the position where the potential energy is 0. But now, when I try and move it on either sides, let us say that from here I move it to this side, by act of doing this I have I am putting in some potential energy into the system, and how much potential energy have I put in? That would be equal to the work done in moving it from here to this point. That much energy is stored in this system as potential energy, so that when I leave it, it will use that energy to oscillate. So, the physics of the problem is simple. So, this is its rest position, it has no energy, no kinetic energy because it is not moving, and it has no potential energy because we have said that at this point the potential is 0. And when I move it like this a little bit sideways, I am putting in potential energy, and the amount of energy is equal to the work done in moving it from here to here, and when I leave it, it will start doing its work. So, the potential energy would simply be equal to the work done against the restoring force. So, that would be something like so, in general when I write in terms of the stiffness constants, it is S times x prime dx prime. So, I need to do this integral. So, so remember that this was our restoring force. So, all I have done is to multiply the restoring force by the distance that it moves, which is dx prime, and you integrate over the entire distance from 0 to x. So, you add these small products of restoring force multiplied by an infinitesimal distance dx prime. So, when you do this, the integral is easy to do, it will be s x square divided by 2. And if I substitute this value of x here, so remember that x is a function of time, it will be equal to s by 2 into a square sin square omega t plus phi. The total energy would be the sum of kinetic energy and the potential energy. All we need to do is to add these two expressions that we have, So, half m a square omega square cos square omega t plus phi plus s by 2 into So, if we remember what we did in the first module, there is a relation between m, omega and the stiffness constant S, which is that omega square is equal to S by m. If we plug in this relation and substitute for S here, this expression can be simplified and it would simply become half m omega square a square, and there will be this sin square omega t plus phi plus cos square omega t plus phi, which will be equal to 1. So, the total energy is I am denoting by E will simply be equal to half m omega square a square. So, you will notice that each of these kinetic and potential energy individually are functions of time, because kinetic energy has this cos square omega t plus phi and potential energy has this sin square omega t plus phi. So, individually kinetic energy and potential energy, they are time dependent. On the other hand, the total energy is independent of time. So, mass, angular frequency omega, amplitude, all of them are constants. So, the total energy is a constant of motion. It does not change with time. So, what we have is an interesting model. Kinetic energy is time dependent, potential energy is time dependent. They change in such a way as to keep the total energy constant. The fact that energy is a constant of motion should also be physically appealing, because in an ideal case where there is no dissipation in the system, then the energy that you put in when you start off the oscillations like this would not be expended at all. So, you would expect that the total energy would simply be converting from kinetic energy to potential energy and back to kinetic energy and so on, but otherwise the total sum of the kinetic and potential energy would remain a constant. And if you go back and look at the equation of motion, you would notice that there is no term in the equation of motion which takes care of the dissipation in energy. So, once again all this points out to the same fact that within the scope of the model that we had written down, there is no way the system could lose the energy. Now, to summarize this module, we started by writing down the equations of motion, which is this d square x by dt square plus omega square x is equal to 0, and motivated by the physical phenomena of say an oscillating particle, we guessed a solution, we corrected it for the dimensional problems, and the most general solution that we could write down was that x of t is a sin omega t plus phi plus b cos omega t plus phi. And then we also saw that given a solution like this, it is straightforward to calculate the velocity as a function of time, acceleration as a function of time. We also saw that there were systematic relations between the values of position, the values of velocity and the values of acceleration that an oscillating system takes. Finally, we calculated the total energy which turned out to be half m omega square a square. And the important part of this total energy is that it is indeed a constant of motion, and it depends only on the square of the amplitude. In other words, a fact that we will keep using again and again later on is that energy of an oscillating system is proportional to square of amplitude. The fact that energy is a constant of motion should also be physically appealing, because in an ideal case where there is no dissipation in the system, then the energy that you put in when you start off the oscillations like this would not be expended at all. So, you would expect that the total energy would simply be converting from kinetic energy to potential energy and back to kinetic energy and so on, but otherwise the total sum of the kinetic and potential energy would remain a constant. And if you go back and look at the equation of motion, you would notice that there is no term in the equation of motion which takes care of the dissipation in energy. So, once again all this points out to the same fact that within the scope of the model that we had written down, there is no way the system could lose the energy.